In this video, we're going to talk about the first of three garbage collection techniques that we're going to look at in detail. The first one is mark and sweep. Mark and sweep works in two phases, and it's called, not surprisingly, mark and sweep. So the mark phase is going to trace all the reachable objects. So when memory runs out and we stop to do a garbage collection, the first thing we're going to do is go and trace out all the reachable objects. And then the sweep phase is going to collect all the garbage objects. And to support this, every object is going to have an extra bit somewhere in it called the mark bit. And this is reserved for memory management. It's not going to be used by anything except the garbage collector. And initially, before we start a garbage collection, the mark bit of every object will always be 0. And then it's going to be set to 1 for the reachable objects in the mark phase. So when we mark an object, we mark it with a 1, and that indicates that the object is reachable. So here's the mark phase. It's going to be a work list based algorithm, and so initially our work list consists of all the roots, so all the initial pointers held in registers. And then while the work list, the to-do list, is not empty, we're going to do the following. We pick some element, V, out of the to-do list. We remove it from the to-do list, okay? And then, this is the crux of the algorithm. If the object V is not already marked, then we mark it. Okay, so we said it's mark bit to 1, and then we find all the pointers inside of it, all right, and then we add those to our work list. Okay, so everything that V points to gets added to the work list. Now, if V is already marked, well, then we've already processed it and we've already added all the things it points to the work list, and so then we just do nothing. There's no else branch here. We just drop it from the to-do list. So once we've completed the mark phase and every reachable object has been marked, then the sweep phase is going to scan through the heap looking for objects that have mark bit 0. And the sweep phase is just going to march through all of memory. It's going to start at the bottom of the heap and walk over every object in the heap and check its mark bit. And so any of the objects that it finds that have mark bit 0, they were not visited in the mark phase and they're clearly not reachable. So all those objects will be added to a free list. And as we go through the memory, there's one other detail that's important. Any object that has its mark bit set is going to have its mark bit reset to 0, so that way it's ready for the next garbage collection. So here's pseudocode for the sweep phase, and this little function size of p is going to be the size of the block, the size of the object that starts at pointer p. All right? And as you'll see, this is actually the reason that we have the size of objects encoded in the object in cool. So remember that in the header for cool objects, there is a size field. That is so the garbage collector, as it's walking through memory, can figure out how big the objects are. Anyway, we start at the bottom of the heap, and while we haven't reached the top of the heap, we do the following. We look at where we're pointing, and then we'll always be pointing to the beginning of an object. So we check to see if the mark bit of that object is 1, and if it is, well, then it was a reachable object. So we just reset its mark bit to 0. Otherwise, if its mark bit was 0, then we're going to add that block of memory, okay, which is the size of the object, to the free list. And finally, in either case, okay, we're going to increment p by the size of the object that it points to, so we point to the next object. And we'll just repeat that loop over and over again, resetting the mark bits of things that were reached and adding things that were not reached to the free list until we've touched every object in the heap. Here's a little example. So we're starting out here with a heap, and we're going to assume there's just one root for simplicity. And here are all the objects. Initially, their mark bits are 0, and we do have a free list, initial free list over here. Notice that there's a little bit of memory that is on the free list. Okay, so after the mark phase, what has happened? Well, we've gone through and touched all the reachable objects. So we started with A, and of course we set its mark bit to 1, and then we followed pointers reachable from A, set the mark bit there, follow the pointer reachable from C, set the mark bit there, and so we wind up with A, C, and E being marked. Nothing else is marked. Okay? And now the sweep phase will go through memory. It's going to reset all the mark bits to 0. And as it finds unreachable objects, in this case B and D, it's going to add them to the free list. And so what will wind up, the free list will wind up being a linked list of blocks of memory that are available for future allocations. Now, this algorithm is very simple. Conceptually, I think it's a very clear how it works. But there are a number of tricky details, and this is very typical of automatic memory management algorithms. And there's actually a serious problem with the mark phase, and this is also typical of garbage collection algorithms. Now, notice that we only run this algorithm when we are out of space. Okay, so the whole point is that we're garbage collecting because there's no more system memory available for allocating new objects. And yet, we have this to-do list, okay? And notice that the work list was not bounded in size. There was no guarantee about how many elements were going to be on the to-do list, and I think it's easy to see that that data structure could actually be fairly large, right? And so we can't just allocate a fixed amount of space for the to-do list or reserve some constant amount of space, but we need to deal with the fact that we actually don't have any space at all when we get around to doing a garbage collection. Now, there is a trick that can be used to maintain the to-do list during the mark phase without having to use any extra storage, and that is to do what is called pointer reversal. So when a pointer is followed, it's going to be reversed to point back to its parent. And this is going to allow us actually to track what elements or what objects in the heap still need to be processed without having to use any extra space. And let's just, if you don't understand that, I'm going to do an example in just a second. I want to mention a second problem as well, and that is, where is the free list stored? And this is a little easier to see how that works. So the free list consists of blocks of memory, and we just use the space in these blocks to maintain the free list. So perhaps the first word or something of the block of memory will contain the size of the block, and then the second word will point to the next block in the list, something like that. But we can use the space in the blocks themselves to maintain the free list. All right, so now let's come back to this pointer reversal idea. Let's say that we have some objects, okay, and we want to track reachability, okay, and we can't maintain the to-do list, all right, in a separate data structure. And so how are we going to do that? Well, here's the idea. Let me change colors. So we're going to come in here, we're going to mark this first object. Let's say this is reachable from the root. And now, or that this is the root, the first object. And now we're going to follow the pointers in this object. And let's say this is one here, this one here is the first pointer in the object. So we're going to follow it, and then we're going to reverse it. We're going to have it point back to the parent. And so now we'll mark this object. And then we'll follow the pointers in this object. Okay, and as we go down, we'll have this pointer point back. And then we'll mark this object. And now there are no pointers in this object. And so we need to go back and process any pointers that weren't covered in the objects that we've already seen. Okay, and how do we find our way back? Well, that's what the pointer reversal was for. So we follow the blue arrow back here. As we come back, we'll restore the original pointer. So we'll get rid of the reversed pointer. There are no more pointers in this object either. So we'll go back one more object. And now, of course, this pointer will go away and we'll restore the original pointer. All right. And now we're in this object and we see there was a second pointer that we haven't followed yet. Okay, and then we'll follow it and we'll reverse it. We'll follow the pointer from that, reversing it. And then we'll mark these two objects. When we get down to this object and we discover there are no additional pointers, we'll be able to use these blue arrows here to work our way back, and we'll restore the red arrows as we walk back up through the objects. So essentially, what the pointer reversal does is it helps us maintain the stack for a depth-first search of the graph. So if you're doing a depth-first search of a graph and you want to be sure that you cover all the nodes that are reachable, then you have to be able to do the backtracking, and the reverse pointers allow us to do that. There's one more tiny issue here with the reverse pointers. So notice that there's a little bit of a problem when I talk about reversing pointers. And let me draw two new objects here just to illustrate the point. Let's say I have a pointer from this object to that object. So when I cross over to the object that is pointed to, what does it mean to reverse this pointer? Well, the space for the pointer is actually in this object. There's no space necessarily for the pointer at all in the object that I'm going to. And so in fact, what's going to happen, let's say if this was part of a chain of objects, okay, and this problem is easily solved. The issue is just an off by one problem. So I have space in this object for a pointer, and I can change that pointer. I don't know if I even have any pointers in this object yet. All right, but let's say this is part of a chain of objects, okay? and that I've walked down this chain to this particular object. So as I pass over to this third object, the pointer that I will reverse is this one, and I will make it point back to the previous object, okay? And then I'm just going to remember this particular object here. I'll keep the pointer to this particular object in a register. So I'll keep the last pointer I traversed in a register, in a pointer to the last object that I came from in a register. And then when I go on to another object, I will use the pointer that I'm traversing in the current object to point back to the parent of the previous object. Okay, so it's just a little off by one problem, and I need one register here to hold on to the previous object that I visited, and then I can reverse pointers back up to the parents and grandparents. All right, to summarize the discussion of mark and sweep, space for a new object is going to be allocated from the free list, a little typo there. And we're always going to pick a block, we always have to pick a block from the free list that is large enough to hold the object that we're allocating. And an area of the size that we need is going to be allocated from that block, and then the leftovers we put back on the free list. So let's say that the free list has a block, and say it has 100 bytes, and then we need an object that has 50 bytes in it. So what will happen is this block will get split up. We'll use this first half, the first 50 for the object, and then this other part with the leftover will get put back onto the free list. And the result of that kind of strategy where we have to find blocks that are big enough, but then we might not use the entire block, is that mark and sweep can fragment the memory. We might wind up with lots of little bits of leftover memory, maybe nothing big enough to actually hold an object, and these blocks, these little tiny blocks, might be scattered all over the place. So it's important actually for mark and sweep to also merge blocks whenever possible. So you have to merge free blocks when possible. So basically when the sweep phase is working on the free list, it needs to recognize when it has two adjacent blocks of memory that are immediately adjacent to each other in memory. So if I have two blocks that are contiguous, what I really want to do is to merge them into one big block and just have one entry in the free list. That's to counteract the fragmentation of memory. Now, one big advantage, and perhaps the biggest advantage of mark and sweep, is that objects are not moved during garbage collection. And that means I don't have to update the pointers to objects. Objects just stay put. They don't move as part of garbage collection. And what this means is it's actually possible to adapt mark and sweep for languages like C and C++. So in C and C++, pointers are exposed to the programmer, so programmers can manipulate pointers and test on pointers. And so you can't move objects in C and C++ because the pointer is part of their semantics. The pointer address, I should say, is part of their semantics. But it is actually possible, and people actually have done it, to build conservative or variations of a mark and sweep garbage collection for C and C++, precisely because the objects don't move.